Okay, related rates, which is really just a fancy name for what we have been doing, and that is well, the chain rule. Okay, so the chain rule to begin with is about about two functions but three variables. Okay, so you could have say so you have variable say x. Remember the compositions, and then the new variable is u, or intermediate variable, and then you have y. Okay, and then you could have f and then g over here. Okay, so that's the notation is frequently used for compositions as arrows indicating how one variable gets, you get one variable from the other. Okay, so that's the composition, and then you can write y is equal to f of g of x, where g is u. Okay. So functions are certainly arbitrary as long as they have the intermediate variable matches in terms of say units. Okay, so a typical example could be what we have seen. Remember that example of having the first function gives you the horizontal motion. So x is time, and u is location, horizontal, and then y is elevation. Okay, so it's also location but vertical. Okay, and then you progress from x to u to y in two separate situations, because the time and location and time say it's actually your trip, and you decide when you be where. Okay, so you have a map and you draw a picture, your path, your trip. But then there is this map which gives you elevation depending on your location, right? So how high is the terrain is in a particular sense in a particular location on the map. Okay, so once again, then the first function might be like x and u, and then you just go forward and maybe like this, doesn't matter. And then the second one is u and y, and then I know the second picture actually is more revealing, and it could be just literally, because this is literally what you see. Well, I mean, at least if you look from the side, the horizontal direction is u, and then the vertical direction is y. So this is, the first graph, x is time, so you cannot really see time. Okay, so that is just how you plan to progress forward along the y-axis. So u could be, for example, how about u is east, and you are going straight east, so this is east. Naturally, time just goes horizontal, and then you have two separate functions in two separate situations until they remain separate until you compose them, and the end result is something of like this. It will be the x time as a function, and and elevation as a function of time. Okay. Which could be, I can't even tell. Certainly, it's hard to imagine how the composition do compositions without actual formula. So that's how it works. That is the theoretical approach, which is the most general abstract approach to functions that are unspecified. When they are specified, the story becomes very easy because it's substitution. Okay, so when two functions substitute one into the other, as long as you keep your variable straight, you just take the mean intermediate variable, that is your second function, you plug it inside of the first function. Okay, that's all there is. So and then up until this point, there's really no calculus, because calculus would have to be something about change and then derivatives. But then you have, and now the two versions of the chain rule is the first one that we saw would be F composition G prime of x is equal to f prime of g of x times g prime of x. So assuming that everything is differentiable. And then the chain rule, the second one is, I always found preferable when you throw out the names of the functions and you only concentrate on the variables. Okay, so because you have, like I said, two functions, three variables, it's already 5 items, 5 names, and then that's formula that I gave you first has all of them appearing, well, actually, in a sense, you have three variables, three functions, because the composition, that's another function. Okay, but if you do the Leibniz notation, you simply know that you need to know the rate of change of y with respect to x, and that is the composition, but it is really expressed in terms of the rate of change of y with respect to u first. That is explicitly, we have the graph over there, and it's multiplied by du dx. Okay, so that's all there is. And there's only three variables present in this one. Easy to remember. Once again, remember the kind of a cancellation thing that you can at least imagine, if not actually carry out. You can imagine as if it is canceling. Okay, so and now practical applications of the chain rule is very important. The compositions are actually more important than the chain rule, and they're the more challenging. So you got to make sure that you got them straight before proceeding to any kind of differentiation. You got to make sure that you understand compositions to begin with. They're important. They will be more important. And so they just keep going. So anyway, practical applications are finding tangent lines. Remember, we discussed the purpose of practical purpose and meaning of tangent line. It is a curved, and as if you zoom in, it looks like a straight line. And then if you're talking about either a mirror or glass curved, then you need to find the tangent line. So you know how this light will bounce, or if it is a curved, what is a good example? Well, how about a baseball bat, and it's curved, so which way will it bounce? If you hit a ball with it, it will once again will be bouncing along a tangent line. And then, well, you can think of other examples. Here, this one is a more general thing, because it's less geometric. There won't be any tangent line, as you can see. But the compositions do appear in a very specific way. Whenever you have, well, let's look at other examples. This is I consider the standard example of compositions. If you want to think about the meaning of compositions and the purpose of compositions, you go to this as a metaphor for you to test new ideas on. But there are others for the same purpose. They're just more different fields. So, for example, the problem that I have is about so one formula implies the other. Okay, so we did this. A balloon is being filled at a particular rate, and then you want to know how fast the radius is changing. Okay, okay, example. So the air is pumped at the rate of 5 cubic inch per second. In a balloon. Okay, and then the question, like I said, is how fast does the radius grow? Okay, so let's be careful about not trying to oversimplify it. We're not saying necessarily that the the air is pumped in the air balloon at a concentrated 5 cubic inch per second, but rather that at some moment of time that was the rate. Okay, so in other words, we know about the air being pumped at one particular moment, and we do not know anything that's happening elsewhere. So we know only one fact about that function, only one. So anyway, let's the word problems challenging usually. So let's do it carefully, variable by variable. Okay, so just as always with word problems, you introduce variables. Okay, so what are the variables? Radius. Okay, how about I call it R? Okay, what else? Time, X, and
Volume.
what?
Your volume.
In the volume. Okay, and volume V. Okay, so let's connect them by arrows. So the volume depends on X, right? So like this. And then separately is the volume also depends on the radius, or vice versa for that matter. Okay, so so that is the dependence, and the dependence that is in the nature of the problem. Now that is the setup. That is pretty much the first. The first sentence of the problem. Now the question is, let's translate, like using this as a dictionary, and now we're translating the problem into algebra, and so we did already. So I just use arrows to indicate once again. So the volume depends on time as it grows, and at the same time there is a dependence of volume on the radius. So what is the question?
It's asking about the radius.
Yeah.
The radius grows.
So can you put it in the language of these variables?
Want to be V over X equals R?
Say it again.
V over X equals R?
V over X. I don't know why. The question is, how fast does the radius grow? So I don't want to answer the question. It's really not that obvious. The question is what is the meaning of the question in terms of these terms, in terms of the new variables. How fast? If we every time we say how fast, what is that we're talking about?
Time.
Yeah, time. But that would be just in time. How fast the radius, the quantity r, is changing relative to time, which is what I was talking about. How fast?
Is it going to be, is the units going to be like inches per second?
Maybe. Yeah, it will be inches per second. Okay, so inches per second. So which means, what is the? So once again, what's the question?
It's asking about the velocity of the.
Yeah, velocity, right.
Increasing radius.
Right. So instead of velocity, since it's not literal velocity, right? Because there is no motion, we're not talking. Well, what's the better word for velocity?
Acceleration.
No. Acceleration is the velocity of velocity. I'm talking about the derivative. How fast is the velocity indeed, but then you can say what is the rate of change of the radius with respect to time. That's how fast. So in other words, we're talking about dr dx. That is the question. Okay, so that is and that's where the inches per second will come from, right? The numerator is inches, denominator in seconds, but we have to say it correctly because it's going to be there. So derivative is going to be differentiation. So we'll get to inches eventually, but we have to set it up first. So that is the question is here. The relation is there. So we did not finish translating because we have some pieces of information have not been used, and this is in particular 5. This one. So the air is pumped at 5 cubic inches per second. How do I translate this into the language of R, X, and V?
V equals 5x.
Almost. That would be a correct answer if the rate was constant, right? So this is I'm not saying this is incorrect. So you're saying 5x, right? That's what you said, 5x, which is indeed, if you look at it, it will be exactly that. If you are pumping the per unit of time x, you multiply by 5, and then you have 5 cubic inches per second. What I'm saying is that there's a more general way to put it, and that is simply dv dx is equal to 5 at the moment. Okay, so it is possible that this rate of change has been recorded at one particular moment of time, and otherwise it's variable. So we only know that at one moment of time the derivative of dv dx is equal to 5, and elsewhere at a different time might be different altogether. So it's just you'll see that it actually matters, not in this necessarily in this problem, but in other problems it will matter. So there's one more piece of information. So this dv dx will help us with this, right? This relation. So we don't know what it is yet, but at least we know it's derivative, right? At one moment, which is kind of weird. If I try to plot this function, all I know is the function. All I know is the value of its derivative. So let me just plot it. So suppose this is the moment. Then I know that the derivative at this moment is 5, which means that it doesn't really mean a lot. It means that the possibility of the possibilities are infinite. The only thing I know that I am crossing this line at the slope of 5. Okay, so it's slope 5, and otherwise what's happening to the left or the right, we don't know. So it's, the possibilities are infinite. So it could look like this, or it could look like that, or whatever. Okay, so, but we don't care. That's the thing about it. We don't really care. We have enough information. So this one is missing. The second piece of information, we need the relation between the volume and the radius. Well, fortunately, in case you don't remember the formula, I have it right here. Anybody remembers how to express the volume of a sphere in terms of its radius?
Is that pi r squared?
Pi, well, first of all, there will be pi, yes. What about r? What's the power of r?
R cubed?
Cube, because cubic inches, right? So the only missing part is the coefficient is 4/3. 4/3 pi r cubed. Okay, so we have, for this function, we have explicit formula, so that's good. And then and for the other function, we have only the derivative. Okay, so the setup is done. So this is the translated version of our function. And now we are ready to solve it. So translated, we started with words, nothing but words and the one number. Now we introduced variables, and we translated. That's on the left, and on the right we translated it into formulas. So 3 variables related depending on each other, and maybe one more. It's like this x, b, r. But the relation that we care about is in fact this. This is. So we assume that we understand these relations as v depends on x, as v depends on r. Okay, we do. And then the only thing that is missing is the one that is for us to find is x. Is x and r on the diagonal over there. Okay, so let's go on and solve it. So every time you have related rates, so quantities related to each other by functions, explicitly or implicitly, and then you're interested in the rates, because how fast, right? How fast, and then you have the derivative. So, well, it's always, the answer is always the same. How to do it, the answer is always the same, the chain rule. So dr dx is, okay, what is it?
Would it be dv dx times dr dv?
No, dr dv, that's right. Dr dv, yes. Okay, so once again, check. Works out, right? Okay, so, all right, so that's dv dx is known. This is known as 5, so we're halfway there. So this one is to be determined. This is 5. We only need to determine dr dv. Okay, the one way to, unfortunately, the unfortunate fact is that we have the, rather than having r as it depends on v, this is what we want. We have as v depends on r, so what do? How do we find dr dv?
Would you solve for r in the equation?
That's right. So, so to find it, solve v equal 4/3 pi r cubed for r. Okay, so r is equal to v, and here we have 3/4, 3/4 pi. Is it? Yeah. 3/4 pi cubic root. Okay. Okay, so then dr dv, we got to differentiate this. What do we do? What do we do with the coefficient?
Would it be all that to the 1/3 power?
Well, if yeah, that's right. So the way to go is to replace the root with a power, 1/3. Okay, and then if we are doing a differentiation of a power, we apply the power formula, right? So first of all, let me just tell you right away that this is not gonna, this thing was not gonna worry us by the constant multiple rule, which has factored that one out. And we differentiate what's left. So v to 1/3 power, what's its derivative?
Would it be 1/3 v to the negative 2/3?
Negative 2/3, right? Negative 2/3. Okay, so that gives us what we care about. It gives us the dr dv. So to be substituted into our expression, that what is hold on, do I have a missing part here? Yeah, I think I have a missing part here, but it will come up now. Okay, so so that this expression then is to be substituted in here into our chain rule formula. Okay, so what is missing is then only the volume is missing, right? So you cannot. The thing is that the answer is turns out to be dependent on the volume itself. That's the formula we have here, and that is inevitable because, as you can see, if you try to analyze this formula, how the radius is changing with the volume, and that is it is not a linear affair, just like dv dx is 5, so it is, you can think of it as if it is growing at a linear pace, but at the same time that's not the case about dv, because you think about it about this. So if I increase the volume by, well, suppose I have no volume, I have a 0, and then I increase the volume by the radius by 1 inch. Okay, so imagine what has the balloon, how much it contains the air. Okay, imagine. Okay, now imagine I have a balloon half blown, and then I increase the radius by 1 inch. You see the difference? So it speeds up per extra inch of the radius. The volume is growing faster and faster and faster. And if you reverse that dependence, that it is actually the opposite. It is slowing down. So anyway, so at volume, say, of v equal to, say, 10, well, let me pick some number that would produce nice results. How about 27? Why not 27? So that we can get rid of the cubic root. So dr dv is 3 over 4 pi 1/3, 27. Okay, let's compute this one just as an exercise, negative 2/3. Okay, so I'm not going to do anything with the first term. It's just a cubic root. Whatever happens to the second one. So I repeat this. Okay, so first of all, the negative sign means what of the exponent? What does the negative sign mean?
One over that value.
Yeah, okay, so it's you say division or reciprocal. It's up to you to find a better word. And what about the denominator here?
1 over 27 to the 2/3.
Yeah, well, okay, so yeah, I just want to identify what the fraction means for exponents. Remember? We just did that transition once. It's cubic root, so yeah. So cubic root. So the square remains square, but negative becomes division, and so let me just write it. So it will be 1 over cubic root of 27 squared. Okay, so this can be simplified a little bit. So you have 3, 4 pi 1/3, and here I have 27. So cubic root of 27 is 3. Okay, so and that will be 1/9. Okay, so and then the answer becomes the answer for our original question, dr dx, is 5 times this number, 3, 4 pi 1/3, 1/9. Okay, we could have accomplished this easier. Well, so that's the answer. It looked a little bit awkward, but that's what it is. We could have accomplished this faster if we did not do well. It is worthwhile to mention that this step over here, we solved before. This step is what created all the mess, in the sense that we had the cubic root and all. Because the original relation was not r depending on v, but it was v depending on r. And we did not need that function anyway. We only needed its derivative. So is there any way to find the derivative of the function of the derivative of the inverse of the function without finding the function? And it is possible also. So that is going to be the next topic. Let me quickly outline that. So what is the derivative of the inverse function? Okay, and we need it for occasions like this. Remember, the problem is primarily, as you can see, the two arrows converge onto v we have a relation between x and r is what we are interested in, and yet we cannot get from x to r by following those arrows. We have to reverse one of those arrows, and that's the extra computation. Okay, so that's one purpose why we care. And then we have a bunch of inverse functions that we still don't know derivatives of. So we did do square root. Square root is the inverse of the square, so that's okay. But any kind of arc sine, arc cosine, and especially the logarithm. Especially the logarithm that we definitely need a derivative for. And that's how we're gonna, once we find the formula, we will just substitute it. It's really not complicated, and you can actually guess before you see the formula. It's probably not impossible to guess what the derivative is. So suppose I have my function y equal f of x, okay, x and y, and then the question, what is the important to be able to ask the question correctly. Okay, and the question is, what is f inverse prime of y? Okay, I hope this helps. So the inverse, so this is a particular value of x, this is a particular value of y, and then where is my inverse function? It has the same graph, remember? The graph of the inverse function has the same graph as the original function, except the x and y are misaligned, not the way we used to. We're used to having x, the independent variable, pointing to the right and dependent pointing up. Okay, so if you ignore that inconvenience, then you don't have to do anything with the graph. You can just as well say that, well, this is x equal f inverse of y. It's the same graph. All you have to do is just to reverse the arrow like this. So we usually go from x to the graph to y. Okay, that's the original function. Or you can go backwards from y to the graph to x, and that's how you have the inverse. Okay. So the question then only becomes, what is the relation between the derivatives? Because now actually we're talking about the slope. We're talking about the slope of the inverse in terms of the slope of y. So suppose this is the slope of the original function, and it is equal to f prime of x. Okay? But now I have to look at the opposite. I have to look at the opposite. So f prime of x is equal to the well, let's just write it in terms of the slope is rise over the run. So this will be, did we use this notation already? So the change of y over the change of x, right? Once you reverse, so this slope of y equal f of x. Once you reverse, you have the slope of x equal f inverse of y. So it is still rise over the run, but this time the rise is delta x, and the run is delta y. Okay, so it just all depends on the point of view. You don't really have to do any computations. You just look at the graph differently. You look at the definition of the difference quotient, the slope differently, and you realize that that happens is just it is a flip. You flip you flip the fraction, and you also flip. Remember how we find the graph of the inverse? We flip the graph as well. So what's the answer to this question?
1 over f prime of x.
Yeah, that's right. 1 over. So the answer to this question is 1 over f prime of x. And as you can see, we keep track of variables very carefully, because the f is originally a function of x, and so it's derivative. And then for the inverse, the function is a function of y, and so it's derivative. Okay, so then the relation between that x and that y has to be what? It's simply y is equal to f of x. Okay, so if you want to now write the equation, then f inverse the longer equation 1 over f prime. Okay, okay, so once again, the inverse function derivative, it is a function of y, okay, and is equal 1 over f inverse f prime of f inverse of y. Okay, this is the formula. So we substitute the inverse function into our derivative of the original function so that the right-hand side would be a function of x. As always, we apply the chain rule here indirectly. It is advantageous to use the other notation, Leibniz notation. So what we're talking about is dx dy. The derivative of the inverse function is dx dy, right? And it is simply 1 over dy dx. Okay? So it's the same formula. Believe me, it is the same formula. But it is certainly much easier to remember. And you can see how you flip, just like with the discussion on the right that we had about the slopes. Rise over the run. Similarly, the resemblance of the rise over the run formula in the Leibniz notation, this Leibniz notation, is helpful because you see how we flip that so-called fraction in order to get the derivative of the new function. And so all you have to do is just to take the reciprocal of the original function. All you have to do, the challenge is hidden. It's not disappear. So this is a challenge to keep track of what your variables are so that the formula would work out and you would not end up with the derivative of the new function with respect to the old variable. So let's verify the formula with something familiar. So I'll pick square. So I'll pick f of x equal to x squared. Okay, so I certainly know what the inverse is. F inverse of y is equal to square root of y. Okay, we also know the answer. We differentiated this one from scratch, so we know what the answer is. So, but let's try to apply the inverse function formula, this one, and then we'll see. Okay, so let me maybe write it like this. I think that this is more helpful. So the original function y equal f of x is equal to x squared, x is equal to f inverse of y, square root of y. Okay, so now we differentiate. In order to get the derivative of the new function, we need the derivative of the old function. So I write f prime of x is equal to 2x. Or you can write dy dx, it's even better. Okay, so then by the formula, I don't want to differentiate square root of y. Suppose we pretend that we don't know the answer. So we use the formula. And we have then dx dy is equal to 1 over what?
Is it in y, terms of y?
Not yet. I just want to apply the formula first, and then we'll sort it out. It's always easier just to not to do anything in your head and just do one step at a time, everything on paper. So nothing is lost, and you don't have to. When you retrace your steps, you have all the record right there. So you look at the right hand side of the second formula over there. It is 1 over dy dx. dy dx is 2x, so it's 1 over 2x. Okay, so it is very simple formula. We just know that it is the job is incomplete, right? Why incomplete? No, we differentiated. We haven't found, but you see what's wrong? Why is this not the answer?
Is it because it's not in terms of y?
That's right. They're absolutely right. Every time you do apply the chain rule or this one, there is one little step at the very end. You have to carry out one more substitution. The formula itself is very simple. And that business that I underline here, that's we did not carry out. It's not hard. In fact, I prefer to do it in 2 steps so that then you appreciate how simple this formula is. And then you just, as long as you keep track of the variables, you know that this is not it. You have to do one more substitution. And so what do? I replace x with
The square root of y?
square root of y, yes. That's what x is, right? Look at it. X is equal to square root of y. That's our inverse function. So I just plug it in, and there we go. Indeed, that's the correct answer. Okay, let's do it one more time. And now I do want to do the logarithm. So, in exactly the same manner, y is equal to e to the x. Okay, the inverse is x is equal to ln y. Differentiate. dy dx is e to the x, right? Now we apply the formula, which is simply the flip. So dx dy is 1 over e to the x. Okay? The last step.
It was 1 over e to the ln y.
ln y. Okay? Turns out there is one more step. Simplification. Exponential function and the logarithm, the relation between them is right in the first line over there. They are inverses, right? So when you compose 2 inverses, first logarithm, then exponential function, what do you get?
Did you say 1?
Not 1, y.
1 over y.
It will be 1 over y. That's the answer. Turns out a very simple derivative of this somewhat complicated function. So it's the logarithm which was constructed from the exponential function, which was itself constructed in some fairly complicated way. It turns out its derivative is simply 1 over y. Okay, so it's really not that complicated. If the original function is simple, then you just you differentiate, flip it over, substitute. Two-step procedure. Sometimes it's more complicated if we're talking about trig functions, for example. Sine x inverse is inverse. That's the trouble with this one. There is no even special name for it. It's simply even the name and notation is simply inverse of sine. Okay, so that's the trouble. And then what happens is that this is where the problem becomes more challenging. This is no trouble so far. We just follow the same pattern, and we have derivative of sine is cosine. Okay, then we use the formula. And then dx dy is 1 over cosine x, right? And then you substitute x being arc sine, cosine of arc sine y. Okay, so there is technically it is the answer, but practically speaking, there's a way to simplify this significantly. So let's simplify it. Simplify, if we know a little bit of trigonometry, we can simplify it with very nice results. So let me simplify it. The standard way of doing it is to look at a triangle with a unit hypotenuse. Okay, and then this is what I'm trying to do is express cosine x in terms of y. okay, where y is sine x. So suppose this is x, okay, the hypotenuse is 1, and what are the other two sides of the triangle?
1.
No, the 1 is the hypotenuse, the other two. The adjacent is, remember trigonometry? If the angle is x, what's the length of the adjacent side?
It's got to be smaller than 1.
It will be, yeah. We know a few things like that. Another place for,
Is it the 45 degree?
no. So this is the same triangle as the one that we have seen before when we defined the trig function. So this is x is the angle, and then what is this? The horizontal part is same as that. Okay, the answer is cosine. Remember, cosine of the angle is the adjacent side over the hypotenuse. The hypotenuse is 1. There we go. Okay? Well, so the other side then,
Sine.
it is sine, right? So this is an important picture on the right, but definitely this one is even more important because that's how we define the trig functions. That little unit circle over there is how we define the function beyond just like 90 degrees. So you keep rotating, and the sine and cosine are being defined, and you have a function defined for every x, positive, negative, going all the way to infinity. But this triangle is convenient because when both of them appear simultaneously, it's the same triangle. It's the same triangle, and look at it. It's definitely the same triangle. And now the question is, again, express cosine x in terms of, wait a minute, where is y? So this is y, right? Y is sine x. So I don't want to. What I want to do is I want to get rid of this, and I don't like what it looks like. It's just too complicated. So I just want to do the substitution part in a more sophisticated way, and then find out a more simplified version of the answer. So cosine x is what we have, and we need to express it in terms of y, which happens to be sine x. So what is the green side, the bottom, expressed in terms of the other one? That again calls for more trigonometry. The relation between these two sides, the green one and the red one. Right triangle. What?
Is it cosine over sine equals tangent?
It is, but no, I don't want to. There's a simpler one. What's the simplest? What's the number one formula in trigonometry? The one that you should remember. Number one, very first formula of trigonometry, the most important one, has a special name.
Pythagorean?
Yes, it is. It is exactly it. I'm talking about the Pythagorean Theorem. So you have a right triangle. The square of one plus the square of the other is equal to the square of the third. Okay, so what we have here is then cosine x squared plus sine x squared is equal to 1 squared. Okay. And then what we see here is that this is y squared. So then, as you can see, cosine x is equal to, what is it? 1 minus y squared square root. Okay, so all of a sudden. And so then the answer is dx dy is 1 over 1 minus y squared. So derivative of arc sine. The derivative for arc sine is this little fraction. Okay? In a similar fashion, you can find the derivative of arc cosine. It will just have plus sign there. So it is when you do any kind of compositions, the substitution sometimes produces with that ugly expression on the right, and it is just a composition of two trigonometric and inverse trigonometric functions. It is just so awful that it's not that awful on the surface. It's at face value it's okay, but if you know for a fact that behind all this trigonometry, the function actually is not trigonometric. Look at it. The derivative is not trigonometric. So why would we do this mudding the waters with trigonometry when the answer is just some kind of algebraic function? Okay, so let's do one more problem on related rates. And this one is kind of fun. You may have seen this problem. It's really sometimes asked for the purpose of. Sometimes it's more like asked in a physics class. A sliding ladder. Have you seen this problem ever? No, like a ladder, and it is sliding. It's leaning against the wall, and then it is sliding. So suppose it's 10 feet long, and with only 2 feet from the bottom. I'm sorry. Actually that part is what we're saying here is the bottom is sliding at 2 feet per second. The bottom of the ladder is sliding 2 feet per second. The ladder is 2 feet long, and the distance is 6. This is 6 feet. So it will be actually variable. If you pull the ladder at the constant rate, it will be well, hold on. What's the question? The question is how fast the top is sliding. So this is. So let me write. So 10 feet ladder. A bottom 6 feet from the wall. Okay, so these are the facts. The third fact is pulled, the bottom of that is pulled 2 feet per second. And now finally the question is how fast is the top moving down? Ever seen anything, a similar problem to this? So with related rates, it's easy actually. It is if you try to things in terms of physics, and then you're going in the wrong direction. Because there is certain issues here. What about the friction? What about the forces here and there? It is quite a complex situation. And where is the center of mass of this? If you go into physics, that is pretty much the dead end. Not to say that this isn't ultimately a physics problem that we just solve with calculus tools. So okay, so what do we do? Once again, the problem is to translate this problem into algebraic language, so that we would have variables and functions, and we can use our tools that we have been developing. So okay, so what are the variables? What?
The current height of the ladder?
No, height the top. Okay, okay, the top. The location of the top. How about we call it y? More variables?
The rate at which it's pulled?
It is fixed, so it's not a variable.
Time?
Time. So time. How about we call it t this time? Why? Because the third variable is x, and what is it? The bottom. The location of the top, the location of the bottom, the height of the top, how high it is, and then the bottom is how far it is from the wall. So this is what we're talking about. This is x, and this is y. Okay. So all right. So now let's translate this. So this is like a dictionary, and now we take the information at the top and translate this into the language of these three variables. Okay, 10 feet ladder, 10 feet object. So how do we translate that? Is a key step. Okay, maybe let's postpone this for a second. Let's take the item. Okay, 1, 2, 3, and the 4 is the question. So I'll start with 2. The bottom is 6 feet from the wall. That is a bit tricky. So how would you put it? You see, it's not x equal to 6. It is x equal to 6 at the moment. Right, because it's not constant. X is moving, so it's at one particular moment it is 6, but before and after it was less or larger. Okay, so let's put it this way. You could say it is like, say, t is equal to t naught or something like that. Particular moment of time. It is. I just don't want to indulge into the new variables. Now it is pulled 2 feet per second at the bottom by the bottom. So the bottom is moving 2 feet per second. So how do we put it?
X equals 6 plus 2t.
I guess you could, but I wanna once again stick with the derivative. It is the velocity or the speed of motion of the bottom. So it's simply dx dt. Once again at this moment, because we might pull it at different pace. Number 4 is the question, how fast the top is moving. So what are we talking about? Velocity of y. What is it? Velocity of y. What?
Is it dy over dt?
Yes, dy dt, the derivative of y. It is to be found, and this is the a key piece of information. Is in the very beginning is that we have a wall, we have a floor, we have a ladder leaned against it. Okay, so and it is 10 feet long. So how do we translate this into the mathematics? Using the picture on left. This is the related rates. So we don't have rates yet, but the x and y have to be related to each other based on the picture. What's the relation?
Are we going to use the
Pythagorean theorem.
yeah.
Yes. Okay. So give it to me.
So it's going to be 10 squared equals
X squared plus y.
X squared plus y squared, indeed. So once again, remember the relation is once again t, and then x and y depend on t, and then they are related to each other as well according to that exact formula. So the Pythagorean theorem is what establishes the relation between x and y. In the meantime, x and y as quantities depend on time. Okay, so this is the kind of a diagram that captures the essence of related rates. In this particular situation, we have a relation, and in the end, we know something about the derivatives, and we need to find. We know one derivative, and we need to find the other derivative, right? So we know dx dt we know, and dy dt we need to find. So remember how we solve problems like this? We did it yesterday. So that's the problem is pretty much ready. So now solution. We take number 1 and what do we do with it?
Use it to find y.
No, once again, it is always possible to use algebra to sort of circumvent some of the more tricky calculus things, such as related rates. But it is actually related rates or the chain rule. But really, it's better to take the route that is straight at the goal, and that is what we did yesterday. Is just differentiate the relation. Differentiate the relation, and the related rates will just fall into your lap. Okay, so differentiate tan squared is equal to x squared plus y squared with respect to what? Well, t, because there's really nothing else. Yeah, with respect to t, that's what we know. That's what we want to know. So, okay, so I just do d dt tan squared is equal to d dt. Remember from yesterday, two functions. X is a function of t, y is a function of t, according to the diagram on left. And two functions equal to each other, then their derivatives also equal to each other. On left, I'm getting what? Derivative of 10 squared? No, 10 squared is 100. What's the derivative?
Is it 0?
It is, yes. Don't hesitate. I mean, if there is no t, if it is a constant, always the answer is always 0. Okay, so differentiate the second one. We split by the sum rule. And now we use the experience from yesterday, so we carefully differentiate these two, keeping in mind that both of them, once again, are functions of t. So, d dt of x squared, what is it?
2x.
Almost. Once again, x, you differentiate x squared with respect to x, that's what you did. But x is a function of t. It's actually the chain rule, what we did yesterday, remember? We are differentiating with respect to t, the variable that's not present there. But x does depend on t. Remember that diagram over there? So, 2x, indeed, if you are to differentiate with respect to t, you get to t through x, so you do start with differentiating with respect to x. But then there is more. Remember what we did yesterday? dx dt. This is the chain rule. Remember what I'm talking about here is the composition from t to x, from x to x squared. Okay, so if I now to differentiate this, I'll have 2x here, but I will also x prime. I will have dx dt over here. Okay. So that's why, and then I have to multiply them. It's the composition of two functions, and a derivative is equal to the product of the derivatives. Okay? Okay, what's the second term?
2 times
dy dt. Okay? So, all right, and then let's substitute. Dy dt is to be found. X is 6, dx dt is 2. Okay, so all the variables are known with one exception, that is that we need to figure out what is y. How do we find y?
you solve.
Yeah, you use that equation again, the Pythagorean Theorem, item number 1. So let me quickly solve it. So it will be 10 squared minus 6 squared, right? Square root. So 10 squared is the hypotenuse, the 6 is the other side, so we're left with 100 minus 36. 8. 8. Okay? So, and that does it, because now we have 6 times 2 plus 8 times dy dt is equal to 0, so dy dt is equal to negative, what is it, 12 over 8. Or negative 3/2. Why is it negative?
Because you're falling.
It's going down. Yeah, the top of the letter is going down. That's how it works. One of more interesting problems from related rates, but there are more, and if we have time, well, maybe we won't. Anyway, so we'll continue next time.